Hey, this is Mr. Hansen. We're going to take a look at the triangle inequality theorem, which states that the two smaller sides have to be larger than the largest side. And in doing this, just like we've been doing with some of the other things we've studied, like triangle sum theorem, you kind of look back to the things you already know to try and discover some new things. So let's look at something we're already familiar with. This is called the segment addition postulate. If this were point A and this were point B and point C, we'd know that AB plus BC is congruent to AC. Hopefully that's familiar to you, and it's a postulate. Kind of makes total sense. There's not a lot of proof going on there. You can just look at it and understand how it works. So what we need to do here is kind of think about this postulate, and if we had like a GeoGebra or some kind of software application, we could take point B and we could kind of bring it up like this. We could raise it up here. Here's the new point B. So this is point B, this is point B prime. And I want you to think about what that does to this side length if we attach those 2 points now, and this side length if we attach those 2 points there. Are the new side lengths that I just drew, are they a little bit longer than the old one that was up here? And hopefully you'll be able to reason out that yes, they are going to be a little bit longer. If you consider this as kind of a perpendicular there, you can use the old Pythagorean theorem that hopefully you remember from a while back to say that the hypotenuse has to be the longest side there. So with that information, let's label these sides. I'm going to use lowercase letters now. Let's just do let's do it right here. We'll call this side X, and this side Y, and this side here Z. And so what we would say is X plus Y, and angle, or not angle, let's do it this way. I'm sorry, my notation's kind of confusing. I don't want to confuse it with it. So we will keep the same. We'll keep A over here and C there. So we can say that A B prime plus C B prime, and then we have AC. AC. Well, the thing that we had before is that they were equal. AB plus BC, they're equal. Well, what do you think now? We call this the triangle inequality theorem. So now AB prime plus B prime C, or CB prime, has to be bigger than AC. Has to be bigger. And there's a neat little experiment that hopefully we had a chance to do in class, where you take spaghetti noodles and you break them up into 3 different sizes, and then you make a triangle out of them, to kind of show that the 2 smaller sizes of the spaghetti would always have to be bigger than the third. Let's just take a look at one kind of problem with this. Let's say I had a triangle with a length of 5, a length of X, and a length of 12. What values can X take? Think about this for a minute. Could X take 100? Let's just kind of draw that out. Here's X is 100. And then here's 5. And here's 12. Do you see how they're not going to quite make it? They're not going to quite fit. So what is the smallest value X can take, and what is the largest value X can take? Well, using this theorem that we had, we said add up the 2 smaller ones, and they have to be greater than the largest one. So let's consider X as a small one for a minute. X plus 5 has to be greater than 12. And this is a simple inequality we can solve. Subtract 5, and X has to be greater than 7. So To make that work, x would have to be greater than 7. Now let's pretend like x is the large one. So 5 plus 12, these are the two small sides, has to be bigger than x. And we add those together, we get 5 plus 12, that's 17. So x has to be less than 17 and greater than 7. Let's just to prove the point, let's put in some values where x is not within this range here. Let's put in less than 17, greater than 7. Let's put in 6. Well, 5 plus 6 is 11. So you'd have 12 here for the long side, and 5 and 6. They just aren't quite going to reach. Okay, so that wouldn't work. And let's put in something like 18 for x. So you have 18 for the long side. There's 18, and then here's 12, and here's 5. That won't quite work either. So that's how you can kind of determine the third side of a, or the possibilities for the third side of a triangle if you have the other two sides.